we could do that because these disks, which I call E1 and E2, before they were where they originally, I mean, they were destroying some things. So, but now remember that these disks, well, down to these curves, and these curves, well, up to time -6, but all the way down to time -8 for E1, for boundary E1, and like to -5 and -9 for E2, every time slice, they're just sitting there as nice circles. So the isotopy, which takes this, you know, this crazy picture and just straightens it up, I want that to be sort of carried through, all the various time slices, say between well, actually, we're really 8.5 here, 5.5. So, okay. So it looks like you're really in good shape because this is really a much simpler picture than we really thought it was. However, we have to pay a price. And the price is that when we did this isotopy, then, remember, at time -8, this original little disk appeared to our critical point of index 0. But when we did this sort of isotopy, well, then that took that disk and turned it into a mess. And this is the picture that we could very well see at time -8. You see, like, here's a sphere, and so this circle here is tubing to this inside sphere, and then out of this is a little tube that swings around to the outside sphere. So you can see the disk is a mess. And it's this nice straight band. If you push it down to the -8 level, it's crashing into this disk. Now, if by some miracle it was disjointed from the disk, well, then we'd be able to do a cancellation, but it's not. So somehow we want to make this band disjoint from, somehow I said things to show this band is disjoint from this complicated disk. And to do that, I look at this curve C2, and I want to disentangle this curve from the tubes that are passing through it. So let's look at just a detail of that. Here's this circle C2, and we saw these tubes passing through. And, well, I mean, you're thinking about this, and, it's late at night, and you say, oh, shoot, why don't we just move it off? And then you say to yourself, well, here's a tube, and here's a circle, and just move this a little bit to a fourth dimension and move it back. But, that would quite work, right? Because this circle here, I mean, sitting here at level -8, but it's, at every time, time slices in forward and backward time, plus or -1, I mean, it's still there, so I just can't reliably move this off. But in fact, I can move it off using what I call the light bulb lemma. And the light bulb lemma is essentially this picture, where you have, just looking at the top part of this picture, this is like what you might see in that time S three-dimensional slice where you have the surface passing through vertically, and here's this tube. But if with a little bit of luck, I can find a path in the surface from this spot all the way down to where it intersects the dual sphere, and that path doesn't cross this stuff, then I can do just like the three-dimensional light bulb theorem. I can just slide this guy all the way down, go around the two-sphere, and then just top it around the two-sphere, and then just bring it back. So this path is maybe some complicated path in the surface. It sort of goes outside the time, the T-8 level. Here's where it goes a priori. But the point is that it's distinctly disjointed in these tubes, because these tubes were part of the disk that bounded C1, and when I just delete that disk, it's still a connected surface. So therefore, using this light bulb lemma, I really can move this guy off. So therefore, I essentially have this picture where this guy is off of this tube. So now I want to take this thing and just move it off into a little corner somewhere, and we can, because this is just. I can just move it inside in this particular picture, send it through here and up and out, and just move it over. I mean, I'm simply using the fact that the union of the core plus the band plus this disk plus this two-sphere it's connected. So I can, and this is living in its own little spot. So I can move it anywhere I want, and where I want is right here. And well, so if I do that, then I'm in pretty good shape because now I can just look at the -8 level, this complicated disk to the standard one. The point is that this band here it's just projection. This band really lives up at level -6, and I'm just putting it there to keep in mind what we need to do to cancel the critical point. But the point is, I mean, this is something we know from three dimensions. If you have S2 cross S1, and you just remove a little neighborhood of the S2, and you remove a little neighborhood of vertical S1, then you're just left with a 3 ball. So here's this S2, and here's this S1, and here's a little neighborhood that just contains the C2. Then what we have is a disk, a circle here, and I'm not bounding a complicated disk. But disks are unique up to isotopy in a 3 ball. So therefore, I can just do an isotopy, which just avoids, the green, the vertical, C2, just take this thing and just move it to the standard thing. And there I am. So, and now we're in really good shape because there's just, now we're in good shape because this isotopy just was totally supported at the -8 level. Our band was up there at -5. So once we're finished isotoping this, we just slide the band down, and now we're ready to just cancel the critical points. And so, so this is the picture, just after canceling this critical point. So anyway, I'm trying to explain in this case how to cancel a critical point of index 0 and a critical point of index 1. And in a similar manner, you could cancel all the critical points of index 0 with critical points coming from the bands at -6, and the bands at +6 can cancel all the critical points of that's critical point of index 1, cancel the critical points of index 2. So that's sort of an outline of this four-dimensional light bulb theorem. So in these last couple minutes, just here are several applications. And one is, suppose we're in S2 cross D2, and you just have a properly embedded disk. Then the boundary of this disk is just a curve in S2 cross S1. If this curve in S2 cross S1 is isotopic to the standard vertical curve, then in fact this disk is isotopic to the standard disk. So a disk in S2 cross S1 is standard if and only if, a disk in S2 cross D2 is standard if and only if it's boundary standard. And using that, I'd like to show that disk 0 of S2 cross D2, modulo disk 0 D4, that's trivial. So in other words, if you have a diffeomorphism of S2 cross D2, then you can isotope it. Well, orientation preserving diffeomorphism, then you can isotope it so that the identity except within some small ball. And so the restriction of small balls, well, that corresponds to an element of disk D4, and so it's an open question as to whether the homotopy implies isotopy for diffeomorphisms of the 4 ball that fix the boundary pointwise. So, and here's another application, which is that if you have 2 smooth disks in the 4 sphere, which have the same boundary, then you can isotope one to the other, fixing the boundary pointwise. As you mentioned, the Cerf-Palais theorem said that disks are unique up to isotopy, but there you have to somehow sweep it in and sweep it out. But you can now do this just fixing the boundary pointwise. So let's just try to put this theorem in a little different context. So in one dimension lower, that is, if you have an arc in, say, the 4 sphere, so that there's these 2 endpoints. Of course, S4 is simply connected, so you can homotop that arc to be just a standard straight arc between these 2 points. But we know that for one complexes of 4 nanovolts, homotopy implies isotopy. So this is one of my general position. So this theorem for arcs in S4, that's just homotopy implies isotopy. This is the theorem for disks, 2 disks in S4. And now if you promote this to 3 disks in S4, that is, if you have an embedded 3 disk, say whose embedded 3 ball whose boundary is the standard 3 ball. If you could isotope that to the standard 3 ball fixing the boundary, well, then that would imply the 4-dimensional Schoenfeld theorem. So actually, I think this is actually, what I just said. If you homotop a 3 ball to standard relative to fixing point, I believe it's stronger. I mean, perhaps equivalent, but I think it's actually stronger, or difficult problem. But certainly applies itself to this problem. Anyway, thank you for your attention. Any questions? Mapping question. So if the tip of the ball was connected, then any diffeomorphism of S2 cross D2 would be isotopic to identity, properly isotopic to identity. No, mapping creates group means 3 means diffeomorphism modulo homotopy. So, I'm just saying, if it's homotopic to identity, then it's modulo disk before homotopic to identity plus isotopic to identity. That's how correct. Not trivial T2. I think that's also correct. Actually, there's a stronger theorem that I didn't mention, actually, which is Hastert-free, which is that if you have two, so the white bulb theorem is conditioned for a sphere to be isotopic to standard sphere in a particular space. But in general, if you have two spheres which intersect a third common two-sphere exactly at the point, and those two spheres, so R1 and R2 intersect G in a single point, and R1 and R2 are homotopic, and pi 1 of the four manifold has no two torsion, then I'm claiming that I can prove that they're in that case homotopy implies isotopy. Thank you for correcting this. This state transfer sphere has that trivial normal bundle. Trivial normal bundle is crucial. I mean, it's a fantastic question, which is to answer the same question for CP2. If you have two spheres that intersect CP2 standard in one point, is it isotopic to the standard thing and Forstall thing? And that's thank you for the trivial normal bundles essential here.
So in some basic problem of coordination, you have this kind of positive result, but some other side negative result we have a lot of questions. And this other some kind of borderline problem of this kind, so that we have a negative result, so that is positive result.
Yeah, that's a great question, which is that, as you all know, there are four dimensions, but there's these spectaculars, one spectacular is only. So there's the next, where for distinguishing spheres, but it's very rare as far as I know, where to say that to give a condition where two spheres are actually the same, and somehow be able to bridge that gap, which is to just find the invariance where that nails down the isotopy equation. That would be fantastic.
Any other questions? Okay, thank you for speaking again.
Our next speaker will be Kenji Fukaya from Stony Brook. He'll speak on equivariant fluid policy.
Thank you for introductions, and thank you for organizers to give the opportunity to talk here. So the main, maybe because this is JDG conference, I must mention a bit about JDG. I think the first paper I wrote was actually published in JDG. It was something like 33 years ago, so kind of one third of the whole history. And probably there are four papers I think probably published in JDG. But honestly speaking, all my papers published in JDG are on Riemannian geometry. And after I turned to J theory and simplest geometry, I still not published any paper in JDG. It is maybe that these papers have a bit lower quality, or but my possible excuse is that after I'm working on this simplest geometry, the paper I like is longer and longer. And I remember that something like 10 years ago when we are working on the Lagrangian planar theory papers, we are finally suggested as a possibility to do some metrics to JDG. But then when we finished it, we found it is something like 1,000 pages. And it's a bit lengthy to publish in JDG. We will finally publish in international planes, but not in JDG. So maybe something that I need to try to simplify the proof of Schütterbrunner curve so that it fits inside of JDG. But anyway, so I want to talk about equivariant, equivariant Lagrangian planar theory. So what I want to consider is X omega. This is a symplectic manifold, and G, a property group, acts on it regarding symplectic structures. And what I want to consider is L is a Lagrangian submanifold, and G invariant. And that is the situation. And something I want to explain in the seven. There is some structures, MK, T, that is a space product of equivariant homology of this L. And this is the so-called AG structure. And so I don't want to talk so much about this definition because it doesn't play so much role in our AG talk, but this is a statement. And the more important thing is that this is compatible with the usual structure, so we have this structure. So this is another non-equivariant version of the AG structure which we could complete in the book I just mentioned. And this is diagram to use. So this is not just one equivariant homology and equivariant homology. So this is MKG. MK. So this is one statement. So you can just do this equivalent values. And the other statement is the other indicator of the when common board. If there is 2, L1, L2, which is the G equivariant, you get like a player homology, under some assumptions like obstructiveness. And this is kind of related to this equivariant homology of the intersection. And this is the kind of individual related to individual pair theory. And let me mention these kind of things are studied by another people, like Hendricks, Lipschitz. But they assume some conditions, and this theorem is incomplete generality. And their approach is much more in line with multiply topology, and our approach is much more topological. And but this is something like equivalent variance, so I want to say a few words about why you are interested in this kind of thing, to become this equivalent story. And one main motivation I have to this is about gauge theory. So gauge theory is the following kind of problem in gauge theory. We consider just two-dimensional manifold, compact without boundary, and we consider just space of branch connections, so that the homomorphism of the fundamental group to say SU2 divided by conjugation. And there is a kind of old problem called the pair conjecture, which concerns somehow in symplectic side concerns some Lagrangian pair theory of this singular symplectic manifold. So this is a singular symplectic manifold. And the problem I'm recently interested in is in a gauge theory kind of question is related to this Lagrangian pair homology in this singular symplectic manifold. And this is supposed to be related to some other invariant called the Sanson homology, which is a more gauge theoretic invariant. But one of the big problems, one of the biggest problems to study this problem is this guy is singular. So to study pair homology for singular manifold is never successful so far. So then there is an idea which goes back to this is a project I'm working on this Aristobal Dani. And I just want to, so this token is only some small part of this. But anyway, so there is an idea which is due to Manuel Escaludwas. And also this is based on even earlier work of this Webb Bushman. And this is a deputy. Then the following, so this is a singular. So the problem is if you want to study this Lagrangian pair theory, but to study it in a single space is extremely difficult. But then there is a known, there are some spaces. Let's say I'll check sigma. This is a smooth